So I emailed you all scores from the exam of Monday. I will return the booklets along with sending you a second email with your choices on your booklet and the solution to your booklet. The booklets, incidentally, have the same questions, they're just in different orders. I'll do that as soon as I got makeup exams, or it's almost over, so probably tomorrow or the next day I'll return them all. And I would encourage you to look at your exam, look at your choices, look at your, what you got right, what you got wrong, what you got right by luck, where you weren't really sure. So basically, analysis of the midterm, it did what it was supposed to do, which is, from my perspective, which is really to give you an early assessment on what you're doing in the class. And it's got good news, bad news. If you did really well on the exam, the good news is you did really well on the exam. The bad news is only, what, 17.5% of the semester grade. So it's not huge. If you did poorly on the exam, of course, it's the reverse. The bad news is you did poorly on the exam. The good news is it's only 17.5% of the grade. So I would encourage all of you to use the exam to sort of prepare for the next exam. There's one more midterm and then a final, which is a double midterm in effect. Just to anticipate, the final exam I think of as half of it, 30 questions of it, being the third midterm that doesn't really exist, and the other half of the other 30 questions on the final exam, having a total of 60, of course. The other 30 is open season on the whole semester. So there's lots of exam credit still to be had. Use what you learn from this one to do as well as you can on the next exams. And I've talked to a number of people, a number of you all, about the exam and typically not doing very well on it. Physics in general, and this class in particular, are about thinking, solving problems, learning to go logically through a sequence of things, apply rules that you develop in one context to a context you've never seen before, or just a different context. And that thinking part distinguishes, it seems, from a lot of other academic pursuits. You really have to think these things through. You really have to understand why acceleration, for example, is different from velocity, and why forces don't cause velocity. You really have to understand it. It's not just that you can memorize it. So for those of you who are used to just memorizing stuff, particularly in a flurry right before an exam, it just doesn't work well in physics, because you'll see things you've never seen before, but you can answer them anyway. It's not, 1492, Columbus sailed the ocean blue. I don't know where to go with that, but if you really understand inertia, one of these very basic things I started this semester with, you can see it in 1,000 contexts, 1,000,000 contexts, and you can be right about it every time you see it. And so that's what I'm hoping you'll all learn, develop in yourselves. And I hope that's what you'll take forward 20 years from now. You'll be able to solve some situation. It may have nothing to do with physics, but it may have to do with just the problem-solving skills you'll learn in a course like this. Any questions or thoughts about the exam? Other things you want to talk about? Anything? Okay. I'm then going to go back to well, 2 cents about zerographic copies, as you'll see. But I got one question left over from you all sending them in electronically. How do positive charges move within objects during polarization if protons are fixed? So this is an interesting thought. So you start, question authority, including me. We talked about polarization. It remains an important thing. It'll pop up periodically forever in this class. But the idea was, again, that if you take a negatively charged balloon, which I developed negative charge on it by having it share unequally with my hair ended up positively charged, the balloon ended up negatively charged. I bring it up to the wall, and I claimed that because that negatively charged balloon is there, the positive and negative charges in the wall shift. The positive charges snuggle up a little closer to the balloon, and the negative charges scoot away a little bit from the balloon. And that is true. I didn't make it up. But it's a good question, like if the positive charges that snuggle up closer to the balloon are the protons, how do they move? Because I even said they're fixed. Well, fixed is all a relative thing. They aren't fixed except that they live inside atoms which interact with each other and push on each other. If you bring negative charge near any material, all the little positive charged things inside will experience forces toward the negative charge. And they will shift their location. Initially, assuming that they were at their that they were sitting there essentially motionless. So I'll treat them as though they're little classical objects, little balls, which is not exactly right. We'll see. If all the little balls, the positives and negatives, are all at equilibrium, which is a word I have used occasionally in this class this semester, I'll make sure I've done it for once and for all, defined it. To be at equilibrium means experiencing zero net force, and therefore not accelerating. So if everything's just sitting there, just pick an object, this gadget, all the pieces in there, we can think of them classically as sitting motionless. Not only are they at rest, but they're not accelerating. So each individual one is evidently at equilibrium, zero net force. If I bring over a negative charge, they're not going to be at equilibrium anymore. There's a whole new charge, there's a new force superimposed on all the other forces. All the other forces added it up to zero on every single particle, but I brought up something new. And all the positive charges are going to want to go towards that negative charge, and they will accelerate toward it briefly. Why briefly? Because as they accelerate toward it, they'll start to summon up other forces within the material. They've moved, and the forces on them the other forces on them, which used to be zero, will stop being zero. So if you bring a negatively charged balloon up to the wall, all the positive charges in the wall, which were sitting there, not accelerating and motionless, will suddenly accelerate briefly while they rearrange, they readjust for a new equilibrium. They'll settle in equilibrium again, but it'll be a new one in which that new force contributes. They'll go back to zero net force, but it's shifted. So they've moved over. And for the positive charges, they move a little closer to the negative charge balloon. The negative charges move a little farther away. The wall, being an insulator, doesn't allow even the negative charges to move long distances. So everybody shifts microscopic distances. And that may seem like it shouldn't matter. Microscopic distances that I'm talking about are fractions of the size of an atom, tiny. And you might think, well, that shouldn't matter. It does matter because there are so many of them. If you shift 10 to the 25th positive charges a little closer, and 10 to the 25th negative charge is a little farther away, even though the effects for each charge is tiny, they add up. Is that okay? Of course, if it's not the wall, instead it's a big chunk of metal, the positive charges still can't move very far, but the negative charges can. Now the negative charges being electrons, some of them can shuttle off to the far side of the metal and will. And that will leave parts of the near side of the metal, one near the negatively charged balloon, will now be without the full complement of electrons it used to have of negative charge. And it will therefore be positively charged. So you can get a more dramatic polarization out of a metal than you can get out of a non-conductor, an insulator. All right? So, some of these questions, there's another thing about physics is that it is self-consistent in the sense that there are 1,000 ways to think about the same problem, all of which, if thought correctly, should come to the same conclusion. You don't generate paradoxes. If you generate paradoxes, two paths to a solution give you different solutions. One or both of the paths has a flaw in it. Okay, the last thing I want to say about zero graphic copiers it has to do with the effect of the pin. If you recall, I sort of finished up Friday showing you that oddly, approaching a heavily charged object with a sharp point of metal discharges the heavily charged object. And it discharges it because opposite charges are pulled out on the metal. It gets polarized, right? So if that balloon, this is like the balloon, it gets negative charge on it. It pulls positive charge around, it polarizes the needle, and actually me, because I'm connected to the needle, and the ground, because the ground's connected to me. It polarizes us all. And it draws positive charge out onto the tip, and negative charge it sends as far away as it will go. Well, the positive charge sitting in that tip sprays off the tip onto passing air molecules and goes over and spoils the charge on the ball and kills it. So that's why there's no spark, right? This is the lightning rod effect that Franklin recognized and that we use. Why don't you get a lot of lightning bolts in a city? Well, if everybody's spraying charge up at the cloud using little points, the cloud loses its charge pretty easily, and lightning is diminished, if not absent. We're okay with that so far? Why does a sharp point spray? And this had to do with a question that hopefully you remember from Monday. If you have a surface and a pin facing each other, and the surface has say a huge negative voltage, and the pin has a huge positive voltage. First off, remember that means the pin having a huge positive voltage, this is a place positive charge wants to go away from, and it will do work in leaving this. The ball having a large negative voltage is a place positive charge wants to go to. It will do work on you going there. It loves to go there. So charge wants to leave the pin to go to the ball, and charge again is always positive, unless I say otherwise, or mess up. Also happens. So this is positive, say 2,000 volts, and that's negative 2,000 volts, just to pick a number randomly. What about the voltage here? Well, the voltage here, and this location has a voltage. It's okay, there's nothing else there, but it's got a voltage anyway. Voltage just says, if you had a unit of positive charge there, and you let that charge go off to far, far away, infinity, how much work would it do on you per unit of charge? And it would leave and it would do work. Or maybe it might be negative work. And it turns out that at this location, the voltage is very nearly the voltage of the ball. Why? Because if you're here and you look over there, you see that big ball covered with negative charge. And it dramatically influences the local environment. This is an environment pretty close to that negative charge. Positive charge would love to come here because I'm pretty close to negative charge. Hey, look at my friend here. Okay? And look over there at that positive charge on the 2,000 volts on the tip. It's tiny. Yeah, it's 2,000 volts, but it's not influencing my life over here midway between these two. It's 2,000 volts there, but here, who cares? Positive charge at this location, trying to go away to far, far away. It's going to be mostly leaving the negative charge on the ball unhappily. It's going to be dragged. You're going to have to drag it away from here because it's going to be primarily leaving the negative charge living on this big ball. And it doesn't care a lot about the positive charge on the tiny tip. It's too tiny. So this location, I'll stop the random stories. This location is pretty much at the same voltage as the ball. Very close. I mean, maybe it's, if this is 2,000 volts negative, this might be 1,800 volts negative. This just didn't contribute much. You okay with that idea? It's a hand wavy idea that you can barely see that positive charge there. You can definitely see the negative charge there to say that the negative charge dominates. But it's pretty correct. So if this location is only 10% of the way from this voltage, how do you get up to positive 2,000 volts on this tip? It does have to go from minus 2,000 on the ball to plus 2,000 on the tip. So where, for example, is plus 1,000 volts? It's not here. It's not here either. It's not here. It's right there. You have to get really close to that tip before the voltage starts going up dramatically, before it becomes a big player in the life of test charges that you put at these places and see how hard they're pushed. So all the voltage change occurs right at that tip. Well, why would you care about voltage change? It's because if the voltage is going up very fast near that tip, that means that as you get closer and closer to that tip, the stored energy per unit of charge is going up like crazy, because that's what voltage measures, stored energy per charge. Electrostatic stored, but it's stored energy per charge. So if it's skyrocketing right near the tip, that means that the tip is getting a lot of energy invested in it in that last little squirt toward the tip. And if you were trying to invest the energy yourself with tweezers, you grab the test charges and you shove them from 1,000 volts to 2,000 volts. And it's only a millimeter, maybe not even that. You must be doing a lot of work in that last millimeter, meaning you're fighting a big force. And that's where I'm going. The electrostatic force on the test charge is big at the same location. The rise in voltage over a distance is big. It's like going up, it's like you're going uphill. This is low voltage. It happens to be negative, but this is low voltage, this is high voltage. That means the energy of the charge, as you move it, I'll have a charge here. As the charge moves from low voltage to high voltage, its energy goes up. That's a lot like if you have a bowling ball and you move it from downhill to the top of O hill, its energy goes up. It's different energy in that case. It's gravitational potential, but it's the same idea. Taking a bowling ball uphill stores energy in it. Taking a charge and going up voltage stores energy in it. And at the place where the energy rises the fastest with distance is the steepest part. Of a hill, it's the steepest part. If the energy is rising really fast, you're going up a steep hill. If the energy is rising slowly, it's a shallow hill. Same with voltage. If you're going up voltage and it's rising dramatically with a millimeter's movement, you're going up a steep electrostatic hill. And you're fighting a serious downhill-ish force. So, long and short of it is, remember electric field? Talked about electric fields push on charge. The electrostatic field, the electric field on a test charge is relatively weak out here where the voltage is increasing slowly with distance. You have to go a long distance before the voltage has come up much at all. But that last little bit, the voltage is skyrocketing, which means you're fighting a huge force backwards, which means the electric field is huge there. So the electric field is enormous right at the tip. And that huge field, which means that every little positive charge around is being pushed ferociously, is what causes them to leap off the tip and jump on air molecules and surf their way to the ball and cancel its charge. So, what should you take away from this? One single thing that's definitely worth taking away is that what are called voltage gradients are associated with electric fields. They're in effect the same thing. I think that's the first time I've used the word gradient. What's a voltage gradient? You're used to gradients in some things. So first of all, a gradient. A gradient is the continuous change of a physical quantity with location. For example, in my example in the book, is like a color gradient. Like from red through the purples to blue. There's a continuous evolution of the color from here to here. It's sold to you as a gradient back in the day when you'd buy rub-on gradients for cartoons. Okay, so there are gradients in things. And a gradient in voltage, which is what I've been waving my hands about over here at the ball, from minus 2,000 volts to plus 2,000 volts, that's a gradient in voltage. The voltage at each location in space is changing. And you can see how fast it's changing with distance. So whenever you got a voltage gradient, whenever you got two locations in space, the voltages are different. And I can illustrate difference by height. So this is, the voltage is going down from the right side to the left side. That voltage gradient is associated with an electric field. And the electric field always points from high voltage to low voltage. So there's an electric field that way. You okay with that? So that means things like 9-volt batteries. You guys still see 9-volt batteries, right? It's they're fading. Everything, all this stuff's fading fast. These are not the 9-volt batteries of my youth. They're chemically different. We'll deal with that in a minute. The positive side is, label it, man. Which one's positive? Yeah, positive. This one's positive. This one's negative. What do those mean? It means the voltage of the positive one is 9 volts higher than the voltage of the negative one. We don't actually know what the two of them are on an absolute scale. It depends, we don't know it. But this one is 9 volts higher. So positive charge on this one would release 9 joules per coulomb in going over to the negative one terminal. It's a 9-volt battery. So 9 volts, 9 joules per coulomb. That means this is 9 volts higher in voltage than that. So a coulomb charge going from this side to that side would release 9 joules. Is that all right? So there's an electric field between them. I claim it's there, it's there. I'm the authority. The voltage is varying by 9 volts over a distance of about 1 centimeter. That is 9 volts in a centimeter would be 900 volts in a meter. That's the electric field between the two, 900 volts per centimeter, per meter. There's actually an electric field there. If you put charge there, it will be pushed. All right? If you're wondering why am I waving my hands about saying that I know the difference between those two, but I don't know their absolute value, it's because I don't know the net charge of this battery. If this battery has a net charge of 0, meaning that if you add up all the charges on it, get my hand out of it, it sums to 0. Then the terminal labeled positive will be at 4.5 volts positive, and the terminal labeled negative will be at minus 4.5 volts. There's 9 volts between them. That's that may not be exactly right, but they're pretty close, and the details don't matter. On the other hand, if this battery is sitting on there while this guy's running, and there are reasons for doing something like this. Sometimes people put electric devices in or on a Van de Graaff. In that case, the negative terminal is going to be at minus like 200,000 volts. And the positive terminal is going to be 9 volts higher than that, minus 199,995. So 91. You can move the voltage of the two, you can move them around, but they remain separated by 9 volts. Is that all right? Okay, so again, the takeaway is, if you have a voltage gradient in a situation, there is an electric field there. And the electric field points from high voltage to low voltage every time. Okay? Why would that ever matter? Because we're going to do flashlights next, and here's flashlights. And I've got a car battery, which is going to be our source of electric power, and I have to explain. I have an old-fashioned light bulb of the sort of Edison era type, and that's going to be the consumer of electric power. So we've got one of each, a provider, and we've got a consumer. This is in effect a disassembled or deconstructed flashlight. And we've got a switch and a gadget that shows us electric current. Let me leave the gadget off for a second just because it's distracting. If I close the switch, the light bulb turns on. So evidently, energy is leaving the battery, going to the light bulb, and it's doing it every second, a continuous manner. So there's energy per second going, which is power. And the power is about 100 watts. So about 100 watts of electric power, which is 100 joules per second, is leaving the battery and going to the light bulb, which is making light and heat. And our job is to explain how that is all happening. And I claim that part of what's involved in this is that when you have voltage gradients, you have electric fields, and those push on charges, and they're actually causing the flow of charge to go on here. So, I've got to start somewhere. Well, let me first sort of look at the system as a whole. I'm going to leave the switch off just so I don't get dazzled here by the bright light. What is going on when the switch is closed? We have what's called a circuit, and it's a circuit just like you would imagine with a race car circuit. The electric charge is going around the circuit over and over. The same charge keeps going by many, many, many times. And what it is doing is it's picking up that charge, and again, it's positive charge I'm talking about. It's picking up energy as it goes through the battery. So it leaves the battery with more energy per coulomb than it arrived at the battery. More energy per coulomb, that's familiar. It's picking up voltage. The voltage is rising in the battery. The charge arrives at the battery at low voltage, and it comes out of the battery at high voltage. How high? 12 volts, because that's standard car battery. So charge enters through this terminal, and incidentally, just for practical information, people long ago adopted a convention where wires with negative voltages, or basically the lowest voltage in a story, are typically black, and wires with the highest voltage in a story are usually red. And it pains me to do anything differently. I can't help it. It's kind of like it's beaten into me for so many years. So the current arrives in current. What's current? Current is charge on the move. The charge arrives at the negative terminal of the battery, which is black here, and the battery does some, I would say magic, but there's no magic in it. It adds energy to every passing charge. And the charge then leaves the battery out of its red terminal 12 volts higher. So it's picked up 12 joules. Every coulomb that went through that battery has had 12 joules given to it. So it's got energy that it didn't have before. So there it is. It's got energy. It goes through the rest of the wiring, and I'll come back to the wiring in a minute, and arrives at the light bulb. And it arrives at the light bulb, let's say, at 12 volts. It came out of the battery at 12 volts. Let's say it gets to the light bulb at 12 volts. Well, it's going to go through the battery, so the light bulb. It goes through the light bulb, and it loses energy. It gives up energy as thermal energy. And we'll have to see why it loses the energy in a minute. And it leaves the other side of the wire that is the light bulb filament at 0 volts. It has lost 12 joules. Every coulomb that goes through that light bulb loses 12 joules of energy into some other form, thermal primarily, and some amount into light. And now the charge emerges from the light bulb having lost its precious energy. Oh no, it's down to 0 again. What can it do? It goes through the black wire back to the battery and does the trip a second time, and then a third and a fourth. And that relentless over and over cycling is present in this deconstructed flashlight. It's also present in real flashlights. It's also present in pretty much every electronic gadget we ever see. Charge is moving around a loop. And it goes through a source of power, such as a battery, where it picks up energy per coulomb. And it emerges from that source at a higher voltage than it entered. And then it goes through the loop and finds some destination where it drops off its energy, and it goes from high voltage to low voltage in that process. And the energy goes into some other form, and it does loop again. And if you break the loop, which is what this switch is doing, you stop the circuit. The charge can't keep going around and round, and that has to do with simple electrostatics. The fact is, this battery has put positive charge on its red terminal here, the plus 12 volt terminal. It's covered with positive charge, and the positive charge happily spread out onto this red wire and spread out onto this crazy knife switch here. It's on there, the positive charge is on there, but it can't go anywhere. It's surrounded by insulators. And no more charge can join it because it'll be repelled. If you try to put more positive charge than is already on that switch and wire, the charge that's already on the switch and wire will push it backwards, and you have to do work to shove the additional charge there, which is to say you have to go to higher voltage. It says, at 12 volts, this is all the charge I will take. You want to send more charge onto me? You better find a source of 13 volts. So there's lots of positive charge accumulated on that switch, saying, well, I'm happy to go somewhere and release energy, but no place to go. On the other hand, this whole other half of the circuit, including the light bulb, is connected to the 0 volt terminal of the battery. And that, sort of, in effect, you can think of it as having negative charge on it, I guess. It is all, the charge is settled in equilibrium here too, and no further charge is going to move there until somebody pushes. And this wire, although it's red in color, actually is at 0 volts. It's not positive at all. When I bring the switch closed, when I close the switch, it's at 12 volts on this side. That's at 0 volts. The difference is an electric field, right? There's a gradient in voltage. There's an electric field here. If I bring this down and I finally close it, now the charges are happy. They're being pushed from the high voltage to low voltage. They go through the circuit again. So circuits are easy to start and stop, no ordinary circuits. You just break the circuit. You put a gap in its conducting loop, and the circuit stops. And so a lot of the on-off switches, the light switches in your house and stuff like that, they're simple. In effect, they have 2 wires, one coming in, one going out, and when the switch either connects those 2 wires or doesn't connect them, and obviously the lights are out when they're not connected. Okay so far? Are there questions at this point? See if there's anybody's. Does the pin in the experiment, this one, have to be conducting? The answer is yes. If it's not conducting, the ball will polarize the plastic, this, but you won't get the huge accumulation of opposite charge on the tip that you need to get that strong electric field. So you need a metal point. And actually, let me make sure that I've conveyed to you basically how xerographic copiers and laser printers work, because you live with them. You use them all the time. That pin spraying charge, sorry I'm going to break the train over here, but I'll come back to it. That pin spraying charge at the ball is a useful concept. If you could see charge, you would see this mist of little charged air molecules, positively charged, spraying out and hitting all parts of the ball. You can use that same idea with either a pin or with a thin wire. A thin wire is almost as good as a pin. It has a huge electric field around it too. And that's what's present in your xerographic copier or laser printer is what's called a corona wire. And occasionally you have to clean the corona wire. So if you've ever had to do that or seen instructions to do it, that's what you're doing. You're making sure that thing has no bad spots on it. It sprays charge, and what they use that for then is to spray charge onto a photoconductor. Remember I said There's a special surface. The other key element in a xerographic copier or laser printer is a photoconductor. It's a material that does not conduct electricity in the dark, but does in light. And they spray charge onto the photoconductor in the dark. And therefore the charge sits there on the surface going nowhere because it can't. And then they expose the photoconductor strategically to light that has the pattern of the document you're trying to print, whether that light came as a camera image in effect from the document itself, or whether it was created by a laser scanning across the surface in your laser printer. It's actually a little laser beam going across the surface and winking on and off so that it illuminates some spots and doesn't illuminate others. They now have a pattern of charge on that surface that looks like the document, except that it's not colored yet. It's just charge. And they use it in the polarization tricks that I've talked about to cause little pieces of plastic to stick to the charge spots. So wherever light did not hit the photoconductor, plastic sticks. And the plastic can be black for classic print, or it can be colors for colored printers. And now you got plastic stuck wherever there was charge. The only thing left to do is to transfer the plastic, this pattern of plastic, onto a sheet of paper. And they do that. They may use light for that. They certainly use heat and pressure, but they get the pattern of black stuff to transfer onto the sheet of paper, and they melt it into the paper so it stays there. But that's basically xerographic copiers, which is the official topic. But even xerographic copiers, the xerographic copiers of the past 50 years, they showed up in the 50s, 60 years. Initially they were all optical. They would have an original document. They would use lenses to project that document onto the photoconductor and erase charge wherever light hit. So wherever there's a white spot on the document, the charge would be erased, no black pigment would stick, and you get a white spot on the paper. Wherever there was black on the document, no light would hit the photoconductor, the charge would remain, the black toner would go there, and you get a black spot on the print. So that's a classic xerographic copier. Nowadays, even that's evidently, people can do it more interesting. They just scan the document with fancy electronics, and then they print the document as though from scratch using a laser printer. So that's how the copier that I printed, for example, the exams downstairs, that's what it does. It's a laser printer with the scanner. There's no optical system at all left. It's sad and boring. But the laser printers are much more common now than anything else. They literally have a laser in them. You now see lasers enough. It's kind of a laser pointer laser. Back in the day, they were very expensive things. Now they're cheap as dirt. So you just get a laser pointer laser with the ability to wink it on and off, and the ability to scan it across the photoconductor very fast as the photoconductor goes by. And you write a pattern of bright spots and dark spots, and thereby erase or do not erase the charge, pick up the toner, put it on the paper. Okay? So, you now know how a laser printer works. I'm not sure it gives you great insight into how to fix your laser printer if it breaks, but knowing something about what's going on inside is good. All right? Returning here to the circuit, the battery circuit. I said I'd come back to the wires, and I also then waved my hands about what the light bulb is doing to extract the energy. And what I want to follow through now, talk about the wires, is wires, although they're electrical conductors, they do allow charge that arrives at one end of the wire to show up on the other end of the wire. But they don't do it for free. They're a toll road, if you will, or not a total freeway. If you want charge in significant amounts to flow through a wire and keep going. Keep doing it, second after second after second. You have to pay for that. What does that mean? It means that, in effect, there's a sort of a frictional effect that's occurring for the charge that goes in the wire. If you put the charge in this end of the wire, you might hope that inertia alone would keep it moving. If you put it in moving at 1 meter per second, you would hope that it would just coast through the wire, unimpeded, and come out the other end. And yeah, the wire's not straight, so it's going to do some curving stuff, but that's okay. It turns out that with rare exception, wires and conductors will not do that. If you want charge to go through them, you have to push the whole way. Basically, inertia isn't, they don't follow inertia perfectly because they have friction-like effects. It's the same thing as if you want to get a wagon to go across this room. You might wish that it would go through for free, so you push it over here and just coast the whole way for free. It doesn't quite. You have to give it a little push every period once in a while because friction is going to slow it down. And that happens in wires. We'll come back to the details of that, but it has to do, structurally, what's going on. It's that the wire is the charge moving happens to have to do with electrons, which we'll come back to, but they hit stuff, and they don't go through perfectly. They're going through a forest of stuff, and they occasionally bump into things, and they lose their forward motion and their momentum, and you gotta keep shepherding them along. So the bottom line is, you need to push the charge through this wire. How do you do that? With an electric field. That's what pushes on charge. So that's all you need. You need an electric field in the wire. How do you get that? You get it with a voltage gradient. The voltage at the entrance to the wire is a little higher than the voltage at the end of the wire. So the charge enters the wire at 12 volts, and it leaves at maybe 11.9. A little bit of the voltage, that is the energy per charge, is used up shoving the charges through the wire. And this effect is in every wire. It's the power lines in your house, the power lines overhead. The charge is put in at 1 voltage and it comes out a little lower in voltage because the wires are, I'm quipping about them being a toll road, but that's the case. And that is a significant problem for power distribution. Something like 7% of, don't quote me on that number, I think it's right. It's within a factor of 2. 7% of the US generating capacity goes into pushing charges through the wires. So if that can be ameliorated, it's a big energy savings. It's important to climate. And this leads to things that you do, ultimately you care about, and it will be changing in your lifetime, trying to reduce that number. Losing 7% of the generating capacity to nothing is, where does that energy end up? As heat. The wires get warm. And it's just lost. Incidentally, this is where cases where you try to push too much electric power through a wire, like an extension cord. I guess you all end up going through the dorm experience at some point or other, and you know just how persnickety the whole operations here is about things like extension cords. Partly this is why. Those wires carrying electric current, they do consume some of the power, and they do get warm. And if you overdo it, you can get them warm enough to start fires, so, which we'll do soon. You probably have noticed, if you're using a cheap extension cord, say with a hair dryer, the cord itself gets warm. Is this familiar to people? Yeah, you can get them nice and toasty. Okay, so this wire is charged, is consuming some electric power. So you start at 12 volts, you get to the switch maybe at 11.9. If I close the switch, we're working our way over. This guy incidentally shows current going by. So I don't know if you can see it from the distance, but if I turn that on, oh, Nah, I don't see anything. Oh, there it is. The little red dots are moving to the left, showing you current's going that way. By the time it gets the light bulb, the current may be down to 11.7 volts. And it enters the light bulb's filament. And the light bulb's filament is designed to be really crummy at carrying electric current. Its job is to be a terrible wire. So that unlike these wires, which charge only a small fee for carrying current through them, current being charged on the move, the wire in that filament charges basically everything they got. You come in at 11.7 volts, the current leaves there at 0.1 volt. All the rest has been consumed trying to shove the electric charges through the wire. How's that the case? The wire is made of tungsten metal, which is not a particularly good conductor of electricity. Why tungsten? Because tungsten, I'm not going to stop this. Tungsten is the element, in fact, the material that has the highest melting temperature of any material except for carbon. Carbon actually melts at a higher temperature than tungsten, but carbon has other disadvantages than a light bulb filament. The original light bulb filaments were carbon, but tungsten quickly took over. So it's tungsten, which is a crummy conductor to begin with, and to make it worse, they make it really thin and very long. So the wire is a little spiral, and often it's a spiral of a spiral. It's a terribly long circuitous route for the electric charge to go through, and the electric charge has to be pushed the whole way and by an electric field, so it loses all its voltage and gives up all its energy, making the tungsten very hot, pretty much as hot as they can make it without dying quickly. And so the charge leaves the tungsten filament with very little energy per charge left at low voltage. It doesn't leave at 0 volts because this wire, the battery we're saying is 0 volts. The charge, this wire will not carry 0 volt charge to 0 volts. It says, what am I, I'm a charity operation here? No, you got to have energy to go through me. So the wire, the charges have to leave the light bulb with a little bit of energy per charge left to pay, you need to be ferried across the river Styx here to get to the battery. So the battery invests 12 joules in every passing coulomb. Everything else eats up some of that energy. The wires do, the light bulb does it wholesale, and the last wires do too. So what I will do on Friday is talk about how does the battery add the energy. And you'll see that it has a lot to do with things we've already seen, like static electricity. Like if you touch two dissimilar materials together, they fight over charge, and one of them wins. The battery's got that going on in spades inside. It's got chemicals fighting over charge, and one of them wins. And we'll look also at what happens. I told you that wires can get hot. We'll get wires hot, or worse. And anyway, see you on Friday.